In this lecture-style presentation, I will be exploring the ground states of the one-dimensional finite square potential well and the three-dimensional spherical potential well, both of which are continuations of cases we have solved in the quantum mechanics class. I will then move on to look at the two-dimensional circular potential well, how it relates to Bessel functions, and how its ground state compares to the previous two. I will start with the finite square well, with width L centered at x equals 0, in order to make solutions either odd or even, so that they must be sine or cosine, not a combination of the two. The potential within the well will be 0, while the potential outside is V0. I will now solve for the wave function using the time-independent Schrödinger equation, as well as the boundary conditions that the wave function must be continuous, as must its derivative, meaning that the function will be smooth. Then we will have that the second derivative of this wave function will be equal to 2m times the potential minus the energy over h bar squared applied to the wave function. So we get that the wave function, given that the potential is 0 within the well and V0 outside of the well, will be a times e to the ax plus b times e to the negative ax for the left side of the well. Within the well, it'll be c sine of kx plus d cosine of kx. And then finally, on the right side of the well, it will be e times e to the negative ax plus f e to the ax. Then we will have to normalize the function, the wave function. So b will become 0, f will become 0, and we can choose either an even or odd function because we know that the well is placed at x equals 0. So I will be using cosine for within the well, and then we can define what we mean by k and a in the wave function. It depends on energy, so that is what we will eventually be solving for so that we know how our energy levels relate. Now we can deal with those boundary conditions that we set, those continuities. Here we have the smooth continuous wave function that we're solving for, and we can set the equations equal to each other at one of the boundaries. I chose at minus L over 2. So we have our ae to the a minus L over 2 is equal to d cosine of minus k L over 2. This will then become ae to the minus al over 2 is equal to d cosine of kl over 2. We can now look at that derivative of the wave function at the same point. We'll have little a times a e to the minus al over 2 is equal to k times d sine of kl over 2. Next, I am going to combine these two functions by dividing them by each other with the derivative on top, just for the way that the function will turn out will be better to work with that way. And we'll end up with a is equal to k tangent of kl over 2. And then, given the definitions of k and a, we can rewrite that into k squared plus a squared, which then, solving through, is going to end up being equal to 2m v0 over h bar squared. we now have two equations with two unknowns. So that means that we can essentially solve for these unknowns. So we've got our a is equal to k tangent k L over 2. We've got k squared plus a squared is equal to 2m v naught h bar squared. And now we can essentially put these into forms that we'll be able to work with better. Essentially multiplying by L over 2 for that first equation, and also multiplying by L over 2, but squared for the second equation. That's going to make it possible for us to define some new variables. So x is going to be defined as KL over 2, y will be defined as AL over 2, and then we'll be able to rewrite these equations into something that we will then be able to solve graphically incredibly easily. And I'll end up using Desmos for that. It's going to be straightforward enough for that. The other thing that we can do is we can see that this 2m v naught L squared over 4h bar squared is a constant. All of those are constant terms. So we end up with this constant r naught that we can plug in. And then we're able to essentially just graph these two equations, one of which is a tangent and one of which is a circle. And we see that there's always going to be a solution to this system of equations because they will always overlap at some point. The next case is the finite spherical well. I will be solving the three-dimensional time-independent Schrödinger equation for a sphere of radius L with negative potential V naught inside the sphere and zero potential outside the sphere. In solving this equation, we know that the YLMs are always the same for all spherically symmetric potentials. This means that we will not need to solve anything for the angular part of the wave function, so we will be only working with u of r, which is the radial part, and that will be a sine of kr when r is less than L, and ce to the ar plus de to the minus ar when r is greater than or equal to L. We can normalize this. We get that c is going to be 0, and we can define our k and a values in a similar, not the same, way that we did in the previous case. Now we can look at our boundary conditions. They're going to be the same as in the finite square well, where the wave function and its derivative must be continuous. So we will be able to solve for u of r at L, setting the two functions equal to each other. We'll end up with these two terms that then we can combine again by dividing. Similar to how we did in the last part, we'll end up with a tangent and a minus 1 over a. This we will end up changing the form of, though, into a over k is going to be equal to minus cotangent kl. And then we can define an x, and we can change that to a cotangent that we can actually plug into Desmos, and then a term here that will end up being dependent on x and a constant. So we'll be able to define our constant r naught again, similarly to last time, and putting that into our equation, we'll end up with minus cotangent of x is equal to the square root of r naught over x squared minus 1. We can now graphically solve our system of equations, and we end up seeing that there's no solutions until the square root function is greater than pi over 2. This means that the potential has to be strong enough for there to be any ground state solutions of the system, because we know that R depends on the potential of V naught. The final case that I'm going to look at is the finite circular well. I'll be solving the two-dimensional time-independent Schrodinger equation for a circle of radius L with negative potential V naught inside the circle and zero potential outside the circle. The two-dimensional Schrodinger equation can be solved very similarly to our three-dimensional one. We'll end up with the Hamiltonian in 2 dimensions with derivatives of psi in both r and theta, and then with that potential and set equal to the energy applied to psi. So we can then solve it with separation of variables, similarly to how we have solved the Schrodinger equation in the past. And that will give us an r and a theta term. So then we will be able to rewrite the Hamiltonian in depending on r and theta separately. And as it's rewritten, we'll see that we'll have these terms that only depend on r or only depend on theta, making it so that then we can solve this quite simply. And in fact, because we know that there's not going to be angular momentum for the ground state, we can set that theta portion equal to 0, and then we only have to deal with the radial equation. And that will end up being minus h bar squared over 2m times 1 over r times d dr of r dr dr plus the potential times r is equal to the energy times r. And reworking that, we end up with a differential equation in a very specific form that ends up becoming the Bessel functions. And we'll see that because we can set these k and a values as we've done in the past. And once those are in and we see the differential equation with those instead of our minus 2m over h bar squared e minus v, then we'll see that form is the differential equations that become the Bessel functions. From here, we'll be able to look at our function r, the radial function, and it'll be a times the first Bessel function of ar when r is less than L, and b times the modified second Bessel function of kr when r is greater than L. And then we have our same boundary conditions based on continuity of the wave function and its derivative. So we'll be able to set our Bessel functions equal to each other, the derivatives of these Bessel functions equal to each other, and from there divide similarly to how we have in the past. I'm then going to define our variable and our constant and relate x to k so that we have a relation for both a and k. I'm also going to use the fact that with Bessel functions, their derivatives are defined as the negative of the next of that Bessel function type So they have that sub 1 instead of that sub 0. And this will make it so that then we can relate some easily, well, relatively easily graphically solved functions of Bessel functions divided by themselves, essentially. And here I have used MATLAB to graph these Bessel functions. This first one is the j1 over j0, and we know that it is changed by a factor, but the property that the function starts at the origin when we relate it to then the k-Bessel function will give us the properties of the ground state. Now we can look at the modified second Bessel divided by itself, and we see that it ends up having an asymptote at y is equal to 0. This means that it will always intersect with the j-type Bessel function. Similarly to how the finite square well always has intersections between the graph of the circle and the graph of that tangent function. So we always have a ground state in those two cases, in the one-dimensional case and the two-dimensional case. But we saw that in the three-dimensional case, if that potential was small enough, we would end up with no solutions. Having solved all three of these cases, I did my best to try to figure out what it was that made it so that the one and two-dimensional cases have a guaranteed ground state, while the three-dimensional case has to have a strong enough potential. But the reality is that these systems are really complicated, and even with what I was looking into, I wasn't quite sure what made this difference. We can see it graphically and we can understand where it's coming from mathematically, but it's hard to conceptualize, and I'm honestly still not quite sure what the difference is between this two-dimensional and three-dimensional state, other than as I was drawing them, realizing that with the three-dimensional state, we can't really draw a representation of it in the same way as the other two, given that it would have to be in 4 dimensions. I have no strong answer of why these cases are different in the way they are, but I think they're really interesting and a cool system to have worked out and understand.